In a parallel circuit, we can have the same three resistors that we had in a series circuit, but we can arrange them in a different order. In our series circuit, notice that all current had to pass through all three if it wanted to get from one end of the battery to the other. That's not the case in a parallel circuit. Current can leave the battery and go through just one resistor and get back. So each of these is their own little independent path. So it's almost like we have three little mini circuits. That's going to have consequences for how voltage and current behave and how they're very different than in a series circuit. This video is going to attempt to explain this. On the schematic, just to make it more clear, we would have some current going through the blue, some current going through the green, and some current going through the orange. And that's kind of like opening up new roads to travel on. So we've got I-40 with its too many construction zones. One of the things that makes I-40 not as terrible to drive is that there's actually another road, I-240. Now, 240 itself has problems. There are many construction zones along it as well. Unlike just adding another construction zone on I-40, we've now given a second path. That's actually going to speed up traffic. So now we're going to see how current and voltage divide up in a parallel circuit using a set of experiments. To keep it simple, we're going to use identical resistors in this video. In lab, you'll use non-identical resistors. Let's see those patterns. As I said in the previous video, it's often quite surprising to students that adding resistors can decrease the resistance. But it's because we open up new roads for current to travel on, or traffic to travel on. So I've got the one resistor circuit here again. Notice what the current of 0.087 and the voltage of about 10. Let's zoom in and look at the resistor itself. What I'm going to do is I'm going to put resistors so that their feet are in exactly the same rows of holes on both sides of the breadboard. And that's going to open up new paths for current to go from the red positive side to the black negative side. And we'll see what happens to both current and voltage across these resistors. Alright, so here's my one resistor circuit. So I've got a voltage of about 9 and a current of 0.087. So I'm going to throw in another resistor. Again, this is in parallel, so I'll put its foot in the same row of holes as the first. Over there and over here. And if we look, something interesting's happened. The voltage has stayed exactly the same. It's still about 9. But the current has roughly doubled. It's now 0.165. And now we'll do the same thing. We'll put a third one in. So this row of holes. That row of holes. And now we're up at still at about 9 volts, but our current's gone up to 0.24. So there's our 3 resistor and parallel circuit. You can see all their feet are wired together on this side, and they are on the other side too. And again, just think of each resistor as a highway And as you open up new resistors, there's more paths for current to flow. If we look at our data, it bears that out. The voltage stayed the same in each case, but the more resistors I added, the more current flew through the power supply. So, how do you calculate resistance in parallel? It's a fairly complicated equation. And we're just going to have to plug in our numbers. And that will end up being, oh, excuse me, these are 1 over RP. I made a mistake. Don't you make that mistake. So we have 1 over RP equals 3 over 1,000. So we just invert it now, and we have RP equals 1,000 ohms over 3. And that, of course, is 333 ohms. So the number has actually gotten smaller than any of my 3 original resistors, and that's because I've opened up 3 new